I'd like to show you how to do problem number 49 in this video here. Problem number 49 describes an arrangement of charges that looks something like this, that involves a 2 nanocoulomb charge, another 2 nanocoulomb charge, a 1 nanocoulomb charge, and then an unknown charge Q at the top right there. And what it says is that this charge here, the 1 nanocoulomb, experiences no net force. So the sum of the forces on this charge equals 0, despite the fact there's a charge here pushing on it. There's a charge here pushing on it, and an unknown charge here either pushing or pulling on it. We don't know what the sign of it is right now, but despite all that, they're claiming that the force on that charge is 0. How would you accomplish that? Well, we can drop back to some basic mechanics and say, look, on the 1 nanocoulomb charge, if the forces are going to balance, we know the sum of the x forces on it must be equal to 0, and the sum of the y forces on it must be equal to 0 as well. These are the conditions for equilibrium, and they must hold in this case as well. So then we can just go through the problem now and identify what forces would possibly be acting on this 1 nanocoulomb charge and see if we can make that work out in some equilibrium equation here. So I'll start by acknowledging these have this charge and this one have the same sign. So this charge here is definitely going to push on this 1 nanocoulomb charge, and I'll label it F2 for the force due to the 2 nanocoulomb charge. This one is also going to push on it, probably in this direction here, and I'll call it F2 as well. Another force to the other 2 nanocoulomb charge. Now I don't know the sign of this Q right here. It's either going to push or pull on the charge. I'll just guess here at the beginning of the problem that it's going to be positive and push on it. So I'll just say it'll be down like that, and we'll call that FQ, the force due to charge, unknown charge Q. So you can see now I have 3 forces on this 1 nanocoulomb charge. I have an FQ, an F2 here, and an F2 here. They're all going to sum to be equal to 0. Now, in order to use the equilibrium equations I've drawn here, I do need to find the x and y components of all the forces, so I will do that now. F2 here has an x component this way. We'll call it F2x and F2y. Likewise for this F2 over here, it will also have an F2x pointing that way and an F2y pointing up that way like that. So I identify the x and y forces of these 2 charges due to these 2 nanocoulomb, these 2 forces due to the 2 nanocoulomb charges here. FQ is all along the y-axis. It's just going to point straight down, so there's no vector decomposition needed there. We'll just leave it sort of in a state like that. Now, we need some angles in here, so we can use some sines and cosines to find these vector components. I think we can find those from the distances given in the problem here. So, if I know this is 3 centimeters and this is 2 centimeters here, using sort of the inverse tangent, I can find out that this is a 34-degree angle, and I think the same thing is going to happen over here. This is going to be a 34-degree angle as well. And if this is a 34-degree angle, this is going to be 34 up here, and that's going to be 34 up there. Now I have a nice angle in those right triangles I can use to find the components of the vectors using sine and cosine. So I'll just start to fill in my equilibrium equation here, maybe skipping a few steps that you can fill in as far as the vector decomposition goes. But if I look at this triangle up here in the x direction, I definitely see a minus F2 times the cosine of 34. That's this x component pointing towards the left. If I look over here, I definitely see a plus F2 times the cosine of 34 degrees pointing this way. You might have been right if you guessed this. It looks like these 2 x components just cancel away, and it looks like they do indeed here, but that's nevertheless, I'll just sort of let that unfold on its own. In this case here, these are the 2 x component forces here. All those are going to be equal to 0. There are no forces along the x-axis on that 1 nanocoulomb charge, so that's it. Now I look along the y-axis here. Along the y-axis, I definitely have a plus F2 times the sine of 34, and I have the same thing over here as well. I have another plus F2 times the sine of 34 pushing up there. And lastly, I have the unknown downwards pushing force of FQ right there, the unknown charge Q right there. I'll just say that's going to be minus FQ, and all that's going to be equal to 0. These are all the y-axis forces acting on this 1 nanocoulomb charge here. What I can conclude here from some of this math here, from some of these 2 equations that I have here, is that it's obviously pretty clear here that these 2 F2s are equal to each other here. So like this F2 here is equal to this F2. It might be a bit awkward to write something like that. And although they are 2 different charges here, I could also write this in here as F2 coming from the right if I wanted to here, and this could be F2 coming from the left right here. In other words, the left 2 nanocoulomb charge and the right 2 nanocoulomb charge. That would make something like this minus F2 right here, and this would be F2 left right here, and so that would sort of translate into these indices over here. There'll be an L and an R in there. So I can conclude that the forces due to each one of these charges on the 1 nanocoulomb charge is the same, and maybe I can get that intuitively without having to work it, but it looks like the math has backed that up. Now I'm in the situation of actually being able to solve for FQ here. Now I can get that FQ here now is something like 2 times F2 times the sine of 34. Now, the only reason I was able to put that 2 in there is because of this statement right here, that the forces due to either of the 2 nanocoulomb charges are the same, and so this F2 is equal to that F2, even though one of these technically here would be a right and one of these would be a left in here. They're the same. So I get a 2 in there. So I'm getting pretty close to figuring out what the answer is right here. And just a couple more steps that will probably lead directly to the solution here. I know that FQ here now is going to come directly from the Coulomb's law, which says that K times 1 times 10 to the minus 9 coulombs. So the force constant times the charge of my charge in question right here times the unknown charge. There's my KQQ. Now the distance between the unknown charge and the 1 nanocoulomb charge looks like it's going to come from over here from the 4 centimeters minus 2. So there's going to be a 2 centimeter distance in there. So this will be 2 times 10 to the minus 2 meters, and that'll be squared in there. All that's going to be equal to the 2. Now what am I going to put in for F2? Well, that's the Coulomb's law force result for the force between the 1 nanocoulomb charge and the 2 nanocoulomb charge. It's either this force or this force, but we've shown algebraically they're equal, so I'll just pick one here. It doesn't matter which one I use. So that's going to be equal to K times 1 times 10 to the minus 9th coulombs again. That's the target charge on here. But now I'm interested in the force due to either of the 2 nanocoulomb charge. So it'll be a 2 times 10 to the minus 9th coulombs sitting in there like that. All that's going to get divided by the distance between the 1 nanocoulomb charge and the 2 nanocoulomb charge, and I think that can come out from Pythagorean theorem here. It'll be the square root of 3 times 10 to the minus 2 meters squared plus 2 times 10 to the minus 2 meters squared. Like this. Where am I getting that from? If I look at this triangle here, it's simply the hypotenuse of this right triangle here that has a side of 3 centimeters and another side of 2 centimeters here. Everything carefully converted to meters. And remember, the bottom of the force equation is the distance square. So I will put a big squared around this bottom here like that and complete my fraction bar. So I have this big equation here, which looks like it's running off the end of the page, but the only unknown that I see sitting in here is Q, the unknown charge. So that 1 nanocoulomb charge will cancel. That 1 nanocoulomb charge will cancel right there. And you can probably work out the rest of the math yourself on your calculator. Get an answer that says, well, the unknown charge then is going to be equal to, the number that you'll get for that, if I plug into my calculator, is 0.68 nanocoulombs. There's what the unknown charge has to be.